Thank you. Welcome to the second screencast on sorting. Last time we talked about the quadratic sorts, the big O of n squared sorts. Today we'll be talking about some slightly more efficient sorts. They're slightly more complicated. The first sort we're going to be talking about is a shell sort, which is an improvement on the insertion sort. It is basically an insertion sort, but a better performance. It's named after Donald Shell, who developed it. It has a divide and conquer strategy of breaking the array into many subarrays, doing insertion sort on the subarrays, and then finally doing an insertion sort of the whole array. And because we do the sorting of the subarrays, that makes the whole array more sorted. And as you recall, the insertion sort on a nearly sorted array is close to big O of n. So by sorting the subarrays, we get better performance on that final insertion sort across the entire thing. So how does it work? We calculate a gap value for the array that we're sorting, and we do a insertion sort on the subarray of that gap. So for example, we chose 7, so we're going to insert the next pos into the subarray that is 7 and 0, and it actually is in the right place, so we don't have to do any swapping. And then we shift our subarray over, and then we shift our subarray over, and then we go. And so now is the first time we do our insertion sort here. So we swap, we swap, we swap, and now because we expand the array size, because now we can in the gap we can consider 0 again. And so now we're going to swap 57 with 75. And then we slide down one more, and that subarray is now finished, is sorted. So now we've sorted all the subarrays with gap 7, so we're going to shrink the gap to 3. And the sequence of gap values is very important in the shell sort, which I'll talk about later. So we now do the subarrays with 3, and we just keep sliding. We do our swap, slide, swap. And then again, we expand the array size. We're going to put the 62 where 75, 57 is in the right place, 55 needs to be where 80 is, 90, this array, again, we add, increase the size of the subarray, sorted, we got to insert the 60, 90 is in the right place, we're going to insert our 70, we're going to insert our 75, and then we're going to insert our 65. And now our gap, we've considered all the gaps, or all the subarrays with gap of 3. And so now we go to a gap value of 1. And now we're just doing an insertion sort on the array. And since the array is almost sorted, it is a quick, there's not that many swaps that we actually have to do. We don't have to do that many insertions. And so the performance is fairly good. And so now the array is sorted. So here's the source code for the shell sort. So we calculate the gap based upon the length of our array. While the gap is greater than 0, we're going to keep shrinking the gap, and we're going to calculate basically gap values. So then we do the for loop, which is going to consider each of the different subarrays starting at gap, and then we just increase it through to the end of the array. And then we do the insert, which is an insertion sort on the table given where we're inserting the position and the gap that we're considering. So here is the insert method. So we take the value at the position, we do the looping to shift the values over 1 to create the space for our insertion. So as long as next val is greater than the item to the left of it, we need to do our swap, or we do our shift. At the end, we insert the next val in the correct position. And then that's it. We've done our insertion sort on the subarray. So what's the analysis for the shell sort? Because insertion sorts on almost sorted arrays is closer to n squared than, or it's closer to big O of n than n squared, we get improved performance by making with our subarray sorts, we sort the larger array almost. So the shell sort, because it is more efficient than our quadratic sorts, it is a good choice for large values of n, and it's much better than our n-squared algorithms we were talking about. So the analysis, or general case analysis, is dependent on the sequence of the gap values, and it has been proven that if you use powers of 2 for the gap, you get performance basically like your insertion sort is n squared. So the actual sequence of gap values is very important. It has been proven that if we use a Hilbert sequence, then we do get good performance of big O of 3/2. And then we get other sequences give similar or better performance. Our particular algorithm of taking half the table size and dividing by 2.2 and then truncating that gives us a pretty good performance. So the next concept, we talked about shell sort. We're now going to talk about a way of a merge sort. So what is a merge? Merge is a process of combining two sequences into a third. And they have a common compare to, so we can keep the order by using the compare to. So we're going to choose which value, the left or the right, based upon their comparison of those two objects. And the sequence and the output sequence will have the same orderedness as the two left and right sequences. So if we have the left is sorted and the right is sorted, the merged will be sorted also. So what's the algorithm for merge? You access the first item in both sequences, left and right, and then while you haven't finished either sequence, you compare the current items, copy the smaller of the two to the output sequence, and then get the next item in the sequence that we used to copy. And then once we have finished one of the two sequences, we then just copy the rest of the sequence into the output sequence. So in the case of sequence A and B, we're going to compare 244 to 324, use the 244, increment the counter, so then we're going to consider 311 and 324, insert the 311, then compare 478 to 324, choose the 324, increment sequence B's index, and 478 versus 415, use 415, then use 478. We have completed sequence A, and so now we just copy the rest of sequence B into the output, and it is sorted because sequence A is sorted, sequence B is sorted, the output is sorted. So for the two inputs, each contain end, we have to move input sequence to the output sequence. So we have to go through n items. So that's the merge time of big O of n. You cannot do a merge in place because you would overwrite the values, so you need additional storage space of n, big O of n. So you need to double the size of the storage, basically. Here's the code for the merge. So we have an output array, a left and a right. We have our indices into the left, right, and output arrays. And then while we loop, while I is less than left dot length and j is less than right dot length, so we're going to move left and right. We then do our compare of left to right, and then we choose which one to use. So we use the one that's less than, so we increment k, we increment I if left is less than right. If right is less than left, we use the right, we increment. And so once we get out of this while loop, we've either exhausted the left or the right sequence. And so the second while loop, if we haven't exhausted left, we copy left to the output. Else, the next while loop, if we haven't exhausted j, or the right one, we copy the right one. We guarantee that one of those two while loops will not execute because we have exhausted one of those sequences in the first while loop. So we can use the merge algorithm, or the merge concept, to sort a unsorted array. What we do is we split that array into two halves, and then we sort the left side and we sort the right side, and then we merge the resulted sorting ones back together, and if they are sorted, and the merge will continue to sort. And so we can then apply recursion to the sorting of the left side by dividing it in half. Continue on down until you get an array size of 1. That array is sorted because there's only one item, and then you can merge that sorted array with the other side and you will sort the entire unsorted array. So here's the algorithm for a recursive merge sort. If the table size is greater than 1, that means you have more than one item. You calculate what the half size is. You allocate another array, right size, you copy the values in there, you allocate the right side, the right array, copy the values, then you merge sort the left, merge sort the right. Once those are sorted, you can then merge the left and the right back into the original table, and you have a sorted array. So let's do a merge sort on this array. We will split it in half. We then are going to do the merge sort on the left side, so we split it in half. We're then going to do a merge sort on the left side, so we split the 50 and the 60. We now have size 1, so now we can do the merge. So we're merging 50 and 60 back in there. They are done, so now we do the merge sort on the right side, split it, do our merge, so we selected 30, copy 45. And so now we can do the merge on these two guys into the one above. So we select 30, check 30 or 45 and 50, we select that, and so now we just copy 50 and 60 because we're done with the right side. We can just copy, and so now we have sorted the left side, so now we need to do the right side. We do the split, we do the split, we do the merge. We then have that, we now do the merge sort on the right side. We did the merge, we did the merge. Now we do the merge of these two arrays together. Select the 15, select the 20, select the 80, copy the 90, and now we can merge these two arrays together. So we select the 15, select the 20, select the 30, select the 45, select the 50, select 60. We're done with the left side, so we can copy the rest of the right sequence, and we have our sorted array. So what is the analysis of the runtime analysis for the merge sort? Basically, you need to move n items from a smaller array into a larger array, so you got a big O of n. And the number of steps that we have to do, the splitting, is basically log n because we're dividing in half. So we have n time effort times log n steps, so it's an n log n algorithm, big O of n log n. So that's an efficient algorithm, much better than n squared. Now, we need that additional space. Each time we divide the array in half, we need to have the additional data, which basically adds up to we need to have twice as much space. We need to double the space required to store all those subarrays. So we need n additional storage space. So we need 2n space. So we trade time for space in some sense. We're adding more memory that we have to allocate to store the division. So here's the code. Again, we're going to recursively call the sort. So we do our base case. If the table length is greater than 1, that means we have to do the split, else we are sorted because we're size 1. Calculate the half, allocate the left table, copy the values into the left table, allocate the right table, copy the values into the right table. We then sort the left, we sort the right, and then we merge the left and the right into the original table. The next type of sort is the heap sort, and it's trying to address the addition of having this extra storage allocation. We don't want to have to create all these these extra array segments while we're doing the sort for the heap sort. So the heap sort doesn't require any additional storage, and as its name implies, we're going to create a heap in the array to help us do the sorting. As you recall, the heap sorts items in the heap, but in the array implementation of a heap, the actual heap array is not sorted, but as you pull things out of the heap, they come out in a sorted fashion. So what's the algorithm for the heap sort? We build a max heap by rearranging the elements in the array, by additionally adding them to this max heap. And once we get all n items in the array into the heap, we can then start removing items out of the heap and putting them on the right. So we start at the left and build our heap from left to right, and then once the heap is finished, we then start pulling things off of the heap and putting them on the right and going to the left, because as we pull them out of the heap, they will be sorted, and because it's a max heap, we pull the biggest items out first. So let's do a trace of this heap sort algorithm. So here's our random array. And so we're going to start by building the heap. We start at the left, so we look at 50, and it's a correct heap. We then add 60 to the heap, and because we're building a max heap, 60 is the child of 50, so we need to swap them. And so now we've restored the heapness of those two items, so we're going to add 45. That is actually correct, because 45 is less than 60. We add 30, 30 is less than 50, so we're good. We add 90. 90 is greater than 50, so we need to swap it with 50. Now 90 is greater than 60, so we need to swap it with 60. And we've restored the heap. So we add 20, and 20 is less than 45, so we don't have to do anything. We add 80. 80 is greater than 45, so we need to swap it. But 80 is less than 90, so we're done. We don't have, the heap has been restored. And then we add 15 to the heap, and 15 is less than 30. I think 30 is the child. But certainly it is the smallest in the thing, so it is in the correct place, and we're done with building our heap. So we have built the heap. Now the array is not sorted, but we have a heap. So now we need to start shrinking the heap, so we're going to pull the root of the heap, 90, and we're going to stick it at the end. And now 90 is no longer part of the heap, so now we have the heap, and now we just have to reheap. So we need to move 15 down, and we're just going to replace the maximum child, so we're going to swap it with 80. And then 15, we need to replace that with its maximum child, which is 45. And so now we've restored the heapness, and so now we can pull 80 out, and then we reheap. And 15 is larger than 50, so we're swapped there. Restored the heap. We can pull 60 out. We reheap, so we're going to replace 20 with 50. And then, 30 is going to swap with 20. And now we've restored the heap. We pull 50. We're going to change 15, swaps with 45. And we restored the heap. We pull 45. And we're going to replace 20 with 30. We've restored the heap, and we pull 30. We reheap because 15 is larger than its child, and then we can pull 20. And then we got the heap, and since the heap size is 1, we have sorted our array by just removing all the items from the heap and sticking them there. So we have sorted the array by creating a heap and then removing the items from the heap, and that sorts our array. And we didn't need any additional space. So the analysis of the heap sort is building the heap. Remember, adding a heap is, each reheap is a log n. We have to consider every item n, so it's n log n. Removing, again, the reheap is a log n. We have to consider each, that's an n log n. So the heap sort is a big O of n log n algorithm. And we require no additional storage as we're doing the reheap. We can do it we're doing the heaping and reheaping. We can do the sort in place. So here's the algorithm, or the code for the heap sort. We have our sort method. First step is to build the heap based on the table, and then we shrink the heap on the table. We have two helper methods: to build the heap given the array, and to shrink the heap given the array. So to build the heap, we start at the left side, n is 1, and while n is less than the table length, we're going to take the child element and calculate its parent, and then decide whether we need to reheap on that. So we're doing the swap, recalculate or reset the parent and child. And so we keep doing that, and we're going to do that until n. So for each item in the array, we're going to add it to the heap and then do our reheaping. So to shrink the heap, we start again at the table length, so we're going to start at the right side. And we're going to loop until we get to 0. So we're going to go from right to left. We swap the root, which is at 0, with n, removing the root from our heap, and then we're considering only the values from 0 to n as being, or n minus 1 as being in the heap. So we're going to loop, so we need to calculate the left child, and if the left child is greater than n, so that means we're past the end, we're at the leaf, we're done. Then we calculate the right child, and then we need to find the max child, which index is the maximum of the two children. So that's what we're doing here. So we got the maximum. So now we compare the parent to the max child. If the parent's less than the max child, we need to swap. If the parent is not less than the max child, we're done, so we can break out of this. And once we do the parent, the max child, we go back up to the loop and we recalculate the left and right children, and so we keep going until we've reheaped. And that is how we're removing the root, putting it in the right place, and we keep looping until we get to 0 and we have shrank the heap to 0 and sorted the array. The next sort that we're going to talk about is the QuickSort. It was developed in 1962. Its idea is to pick a value called the pivot and then rearrange the array such that all the values that are less than the pivot are to the left of the pivot, and all the values that are greater than the pivot are to the right of the pivot. And then you run the sort on the left side and the right side. And eventually you'll have a sorted array. So it's a recursive, and we're trying to, in best case, we're going to pick a pivot that's in the middle so that we can divide the array in half and get that log n performance. So we choose a pivot, and in any case, you could just arbitrarily pick the left one, the leftmost one, the first one. You want to pick a pivot that is in the middle of the values in your range. But if you scan the range and calculate the middle, that's scanning, it's going to cost big O of n, which you don't want to do that. So you can pick the left one, that's fine. Another twist on it would be you take the left and the right and the middle, and take the middle value, whatever the middle value of those three is, and that's a good choice, generally a good choice. But you choose a pivot. You then are now trying to scan to find values that are greater than the pivot, and they're on the left, and ones that are less than the pivot on the right. So in this case, 75 is greater than the pivot, 30 is less than the pivot, so we want to swap those values. And then we're going to keep scanning until we find the same situation where we have 55 is greater than the pivot, and 12 is less than the pivot, so we want to swap them. And now we keep scanning. Once down passes up, that means we have made sure that all the values less than the pivot are to the left, all the values greater than the pivot are to the right. So now we can swap 44 with 12, and 44 is now in the right place in this array because all the values to the left of it is less, all the values to the right of it are greater. So we have sorted 44, and now we can do QuickSort on the left side and do a QuickSort on the right side. So we're going to QuickSort the left array, and in this case the pivot 12 is less than, so we're done. So that we're now going to do a QuickSort on the right subarray, and in this case we don't have to do any swapping, but we do want to swap the pivot with 23 because that's where 33 belongs. And so now we're going to QuickSort the left subarray, which is 23, and the right subarray was 23, but since they both have a size of 1, they are sorted, so that left side of 44, has been sorted. So now we consider the right subarray of 44. Again, 55 is not a good, is a pivot because it's less than, so we don't actually do much dividing. So now we're going to QuickSort the right subarray, and in this case they're both greater than 64, so 64 is in the right place. So now we do this right subarray again, and now we got to swap them because 77 needs to swap, and then we can quick sort 75, but since its size is 1, we have finished quick sorting this array, and so we have our sorted array. So what's the algorithm for the quick sort? If first is less than last, we have an array, so we can continue on. We partition the elements in the subarray from first to last, such that the pivot value is in the correct pivot index. We choose the first item as our pivot, and then we quick sort first to pivot index -1, so we're going to do the left side, and then we quick sort pivot index +1 to last, which will quick sort the right side. If the pivot value is random, then statistically half the values in the array will be less than the pivot and half the values will be greater than the pivot, and the pivot value should be in the middle of the array, thus dividing the array in half and therefore giving us our log n performance. If they have the same number of elements, we got it log n levels, that gives us our log n, and because we have to choose the n pivots, we have n moves, so the quick sort is n log n, just like the merge sort and the heap sort. Just like the merge sort, actually, because we're doing the same sort of division, but it is in place, like the heap sort. Now, however, if you get bad pivot values, if you don't do the partitioning, or if you end up with a partition size of 1, so you're actually only pulling one thing off, you then get the case where you actually don't get the log n levels, you get n levels, and that becomes a big O of n squared. So, and because it's a recursive algorithm, the overhead of the recursive call, the runtime stack, storage, all this stuff makes the quick sort very poor relative to our very simple bubble sort or insertion sort, which don't have the overhead of the call stack, n recursion calls, plus all the memory that you're going to use up by causing the recursion and the activation stack, the copies of n of the arrays. So if you have the case where you're doing a sorted array, you have a sorted array, you don't want to use QuickSort, it's much more efficient to use something like the bubble sort. So here's the QuickSort code. Since we're using recursion, we need to have a helper, recursive helper method that provides the first and the last. So we're going to run this recursive method, given table, and 0 in the length, -1. And so we have the recursive method. Again, if first is less than last, we still have values that we need to do our sorting on. We partition the array from first to last, returning the pivot index of where the pivot is, and then we quick sort the left side, quick sort the right side, and we will have sorted the array. So what does partition do? Partition remembers the first value, which is our pivot. It puts up and down, and then so we're going to move up. We're going to increase up until we have about, as long as we are less than the pivot, we'll increase up, and then we will move pivot or down, as long as the pivot is less than the value. And then if up is less than down, which means we found values, we then swap them. And this is a do while loop, so we're going to keep doing that until up and down have crossed. Once they have crossed, we know that down is pointing to the pivot index, so we're going to swap the first value, the pivot, with down, and then we're going to return down, which is the pivot index, and then we can do the quick sort of the left and right. So this is the grand slide of all the comparisons of the performance, number of comparisons for our sorts. You remember the quadratic ones. Selection sort is very consistent. It's big O of n squared on average, best case, worst case. Again, the bubble sort, if you detect that you did no swaps, you just had to do that one scan through the array. So the best case is a big O of n. Same thing with insertion sort. You run through once, you did no swaps, you have done a big O of n. On average, our quadratic sorts are big O of n squared, and in worst case, they're big O of n squared too. So very consistent. The issue really is that big O of n squared for large n is terrible performance. The shell sort, best case, you get almost big O of n. Average case, not quite as good, but better than n squared. And then worst case, you're at a big O of n squared. Our merge sort, n log n all the way across. The one caveat is you got to remember that we have to allocate more storage for the merge sort. Heap sort is big O of n log n, slightly slower than the merge sort because you do the reheaping twice, but you can do it in place. So that's a very nice sort. And then the QuickSort can be quick. On average, it's quick, but in the worst case, it is very expensive. It's actually worse than our quadratic sorts because of the overhead of the recursion and the extra additional storage caused by the recursion. So it'd be a good idea to have a sense of this table when you ever have a problem, a sorting problem, which sort to use. If your n is small, you might as well try one of the simpler insertion sort. Very simple to write, very simple to use. Java uses the merge sort and the QuickSort in its collections, so they chose those because in general the performance is good. Thank you very much for your attention.